So today I will try to solve the analysis of trusses over here. It is the truss problem. It is one of the most important problems as far as Ansys laboratory is concerned, and also in the VTU question paper in the final examination of finite element method. It is one of the important questions over there. It carries 10 marks. So I will try to solve it over here. So this is the truss problem, and the number of elements are 4 in this particular problem. That is 1, 2, 3 and 4, and these are the nodes. That is 1, 2, 3 and 4. And I have written here the nodal displacement, that is u1 and v1, that is x displacement and y displacement. So here same like that, u2, v2, these are the nodal displacement, u3, v3, u4 and v4 are the nodal displacement over here. And this is the length is given 4 meter and y distance is the given here 3 meter. So first of all you have to write the nodal data, the x coordinate and y coordinate of nodes, the first node, second node, third node and fourth node. First node is this, second is this, third and fourth. So for first node, x coordinate is 0 and y coordinate is 0 over here. Then for second node, x2 is 4, that is 4, y2 is 0, that is 0. Then for third node, x3 and y3, that is 4 comma 3. So I have written it here is 4 comma 3. Then for fourth node, 0 comma 3. So 0 comma 3 I have written over here. Then element connectivity table. So you have to write the given data for the elements over here. So for first element, the initial node is 1 and final node is 2. So 1 and 2 I have written it over here. Then for second element, initial node is 2 over here and 3. So 2 comma 3. For third element, initial node is 3 and final node is 1. So 3 comma 1. Then for final element, initial node is 3 and final node is 4. So 3 comma 4 I have written it over here. Then for calculating length of the element LE, so there is a formula for this length of element. So LE1 for first element, there is a formula under root of x2 minus x1, that is x2 minus x1 and y2 minus y1. So x2 minus x1 whole square plus y2 minus y1 whole square is equal to under root of, what is the value of x2? That is 4 over here, 4 meter, that is x displacement. So 4 minus x1, x1 is 0, 4 minus 0 whole square plus 0 minus 0, that is y2 minus y1, 0 comma 0, that is 0 minus 0 whole square, which will be equal to 4. Now for second element LE2, that will be equal to, for second element, that is x3 minus y3, then x2 minus y2. So x3 minus x2 plus y3 minus y2 whole square. So I will try to put the values over here. So x3 is given, x3 is 4 minus x2, that is 4. So 4 minus 4 whole square plus y3 is 3 and y2 is 0, which will be equal to over here, 4 minus 4 is 0, 3 minus 0 whole square, that is 9 under root of 9, that is 3 over here. Then for third element, so initial node is x1 and final node is x3. So x1 minus x3 whole square plus y1 minus y3 whole square. So just put the values over here. So x1, that is 0 minus x3 is 4 over here whole square plus y1 is 0 minus y3 is 3 whole square, which will be equal to, that is 4 square plus 3 square, that is 16 plus 9, that is 25 under root of 25, that is 5. Then for fourth element, LE4 is equal to under root of is final minus initial. So x4 minus x3 whole square plus y4 minus y3 whole square over here, which is equal to under root of x4 is 0 minus x3 is 4 whole square plus y4, that is 3 minus y3, that is 3 whole square, which will be equal to 4 square, that is 16, and this is 0, so it will be equal to 4 over here. So it is the length of elements. So just put these values in this particular table. So 4 3 5 4, 4 3 5 4. So this table is over. Now the left things are L and M. So how to calculate M? There is another formula for this L. So L is equal to x final minus x initial divided by length of the element. So I will try to solve for each and every element over here. So for first element, L1 is equal to x final minus x initial divided by length of element 1, which will be equal to, for first element x final is x2, that is 4, minus x initial is 0, x1 is 0, divided by LE1. We have calculated it over here, LE1, that is 4. So 4 upon 4, that is 1. So L1 is 1. Then L2 is equal to same x final minus x initial divided by LE2, which will be equal to, for second element, so x final is 4 and x initial is 4. So 4 minus 4 divided by LE2, that is 3 over here, so which will be equal to 0. Then L3 is equal to x final minus x initial divided by LE3, which will be equal to, for third element, so x final is this, that is x1, which is 0, minus x initial, that is 4, upon LE3, that is 5 over here, which will be equal to minus 4 upon 5, which is equal to minus 0.8. Then L4, which will be equal to x final minus x initial divided by LE upon LE4, which will be equal to, for fourth element, x final is 0 minus x initial is 4 upon LE4, that is 4 over here, which will be equal to minus 4 upon 4, which will be equal to minus 1. So this is the L1, L2, L3 and L4. So you have to put it in this table. So this is 1 0 1 0 minus 0.8 and another one is minus 1 over here. Then we have to calculate the last part, that is m. So how to calculate? There is another formula. So m is equal to y final minus y initial upon LE1. So for first element, that is m1, which is equal to y final. For first element, y final is 0 minus y initial is also 0 upon LE1, that is length of element 1, which is given 4, which will be equal to 0. Then m2 is equal to y final minus y initial upon LE2, which will be equal to, for second element, y final is 3 minus y initial is 0 upon, that is length of 2, that is 3, so which will be equal to 1 over here. So same like here, for third element, m3 is equal to y final is 0 minus y initial is 3 upon length of element 3, which will be equal to 5 over here, that is 3 upon 5. So 3 upon 5, which will be equal to minus 0.6 over here. Then m4, which is equal to, for fourth element, so there is y final is 3 minus y initial is 3 upon length of element 4, that is 4 over here, which is equal to 3 minus 3, that is 0. So we get the values of m1, m2, m3 and m4. So that is 0, 1, minus 0.6, 0. So put it in the table, in this particular table over here, that is 0, 1, minus 0.6, then 0. So the table is over. Now after that, we have to calculate the stiffness matrix for each and every element. So for first element, stiffness matrix is given by that is K1 is equal to A1E upon LE1 into, there is a formula you have to remember. So I will tell you the easy way how to remember it. So first write the L square m square in the cross manner, and then LM and LM in the another cross manner. Then you have to just opposite the signs of the particular terms over here. So this will become minus L square, this will become minus LM, same here, minus LM minus m square. Now in the first row, whichever is the a positive element over there, you have to take negative in the third row. So L square is positive in the first row, you have to take it negative it over here. So minus L square minus LM L square, so it is LM. Then in the second row, whichever is the positive term, you have to take it in negative manner. So it will become minus LM minus M square. Whatever is the negative in the term, you have to take it positive. So LM and M square. This will become your stiffness matrix for the first element. Now you have to only put the values. So K1 is equal to it is given, area is given in the particular formula. So area is 0.1, it is in the problem, it is given. So area is equal to 0.1 meter square. So A is given, and also Young's modulus, it is also given. E is equal to 210 gigapascal. So you have to write it over here. So it will become A area is 0.1 into E, that is 210 into 10 raised power 5 upon length of element 1, it is also given. So which will be equal to 4 over here. See here, length of element 1, that is 4. So 4 into what is the length, it is also given in the table. So you have to take this L for this particular formula. So L is 1, so 1 square, that is 1. Then 1 into M, M is 0, so it will become 0 minus L, that is minus 1, LM, that is 0. This term also 0 0 0 0. Then minus L, that is minus 1, LM term is 0, L1 is 1 and LM is 0. Then the fourth row will become 0 0 0 and 0. And you have to put nodal displacement over here, that is for first element u1 v1 u2 v2 u1 v1 u2 v2. It is in the first element, you can check it over here. U1 for the first element u1 v1 and u2 v2, so that I have written it in the stiffness matrix over here, that is u1 v1 u2 v2 u1 v1 u2 v2. So for this is the first element. Then we take for the second element. So K2 is equal to A2E upon LE2, same formula, L square LM minus M, sorry, plus M square minus L square minus LM minus LM minus M square. Then minus L square minus LM, L square LM, then minus LM minus M square LM and M square over here. Then you have to put the values. So K2 is equal to 0. K2 is equal to, area is 0.1 into 210 into 10 power 5. Sorry, this is 9 over here. If in terms of meters you have to take, so 210 into 10 power 9. Same in the first element, you can take 10 raised power 9 over there. So divide by, that is LE2. So length is, second length is given, that is 3 over here, 3. Then same here, you can calculate it. What is the value of L? L is 0 over here, 0 0 0 and 0. Then this will become 0 and M square. So M is 1, so 1 square is 1, that is 0. The minus M is, that is minus 1. Then again 0 0 0 0. LM, it is also 0, which is equal to minus 1 0 and 1 over here. So it will become your matrix. Then if I try to solve it in the calculator over here, so let me calculate it. So it will become 0.1 into 210 into 10 power 9 upon 3, which is equal to 7. That is K2 is equal to 7 into 10 power 9. Remaining thing is same, 0 0 0 0 0 1 0 and minus 1 0 0 0 and 0 0 minus 1 0 and 1. So it will become your second stiffness matrix for second element. And for third element, stiffness matrix is K3 is equal to, I will write directly values over here, that is 4.2 into 10 power 9. Then the matrix will be 0.64 0.48 minus 0.64 0.48 but minus, so then 0.48 0.36 minus 0.48, then 0.36 minus. So directly change the values of these terms over here, that is minus 0.64 minus 0.48 plus 0.64 plus 0.48. Then write these positive terms as negative in the fourth row, that is minus 0.48 minus 0.36, and these negative as positive, so 0.48 and 0.36. so this is your third stiffness matrix for the third element. If you look here for the third element, there are the nodal displacement u3 v3 and u1 v1. so I will write it over here, that is u3 v3 u1 v1, u3 v3 u1 v1. Then for another element, fourth element, so k4 will be equal to, that is 5.25 into 10 power 9. so the matrix will be, that is 1 0 minus 1 0, then 0 0 0 and 0 minus 1 0, 1 0 0 0 0 and 0. so this is your stiffness matrix for fourth element. If I will show you the fourth element over here, this is the fourth element. so nodal displacements are u3 v3 and u4 v4. so write it here, u3 v3 u4 v4, u3 v3 u4 and v4. now we have to calculate the global matrix. so when you draw the global stiffness matrix, so it is a matter of concern for every student how to draw the what we call this global stiffness matrix. I will tell you in this video as far as possible for me, as in the simple manner I can tell you. so I will just write here the global stiffness matrix, global stiffness matrix. So before proceeding for the global stiffness matrix, see in the figure there are 8 nodal displacements, that is u1 v1 and u2 v2 u3 v3 and u4 and v4. if there are 8 nodal displacement in the problem, so we can draw the 8 cross 8 matrix. so I have drawn it over here, that is u1 v1 u2 v2 u3 v3 u4 v4. these are the nodal displacement in the row wise and column wise, u1 v1 u2 v2 u3 v3 u4 v4. now you have to draw these stiffness matrix of all the elements in this particular global matrix. so I have calculated the values of these particular matrix, that is k1 k2 k3 k4. you have to draw these matrix in the global matrix. so I will draw k1 as it is, that is 5. this matrix I will draw the whole in this particular global matrix, that is 5.25 0 minus 5.25 0 0 0 0 and 0 minus 5.25 0 5.25 0 0 0 5.25 and 0. so this is the k1 matrix. I have drawn it here. then for k2 we have to draw only this first part, square part, u2 v2 u2 v2. so you have to search in this particular global matrix u2 v2 u2 v2. so it comes under this particular row and column. so just add it over here, that is 0 0 0 and 7. so add it here 7. then this part 0 0 0 minus 7, it comes under u3 v3 u2 v2, that is u3 v3 u2 v2. so it will come over here, that is 0 0 0 and minus 7 over here. then the third part of this matrix, that is 0 0 0 minus 7, that is a u2 v2 and u3 v3. so u2 v2 u3 v3, so it will come under this column, that is 0 0 0 and minus 7. then after this last part of this second stiffness matrix, that is 0 0 0 7, it comes under u3 v3 u3 v3, that is u3 v3 u3 v3. so it will become 0 0 0 and 7. now the third stiffness matrix, that is k3, for first this what we call as the square element, so it comes under u3 v3 u3 v3. you have to add it over here, u3 v3 u3 v3. so it will add up over here, that is plus 2.68 and 2.01, then plus 2.01 and 1.51. so then after the second part, u1 v1 and u3 v3, u1 v1 u1 v1 and u3 v3. So it will come under this particular column over here, that is minus 2.68, minus 2.01 and 2.01 and 1.51 minus. So then third part of this particular matrix, that is minus 2.68, 2.01, it comes out under u3 v3 u1 v1, that is u3 v3 u1 v1. So it will come under over here, that is minus 2.68, minus 2.01, minus 2.01, minus 1.51. Now the last part of this third matrix, that is u1 v1 and u1 v1, it comes under, this part comes under u1 v1 u1 v1. So u1 v1 u1 v1, it will add up over here, that is plus 2.68 and 2.01 and 2.01, it will add up here, that is 1.51, it will add up over here. Then the fourth matrix, that is u3 v3 u3 v3, so it will come under u3 v3 u3 v3, it will add up over here, that is 5.25. rest numbers are the 0 over here, so no need to write. Then u4 v4 u3 v3, u4 v4 u3 v3, so it will come up over here, that is minus 5.25, 0 0 and 0. Then after u3 v3 and u4 v4, this part u3 v3 u4 v4, u3 v3 u4 v4, so it will come under this minus 5.25, 0 0 and 0. Then u4 v4 u4 v4, 5.25, this one 5.25, 0 0 and 0. Rest of the what we call rest numbers can be 0, can be written as 0 in the particular global stiffness matrix over here. Then it will become 0 0 0 0 0 0 0 and 0, same like here 0 0 0 0 0 0 0 0. So this is your whole global stiffness matrix. After that, and also 10 raised power 9 is over here, 10 raised power 9 for the each and every element. So this is your global stiffness matrix is this. Then after, you have to apply boundary conditions and the equilibrium equation.